So I'm going to talk about some a brace of papers. Some of this was done with my students, Pralay Chanda and Sai Hamdan, and also sort of my international collaborators, 2 from South America and 1 from Iran. And basically, I want to talk about a set of issues. I don't want to talk about one single framework so much, but I wanted to really talk about the interplay between cosmology and dark matter. So, sort of the way you're brought in, graduate students are often brought into thinking about dark matter is you write down your particle physics model, and then you can calculate the relic density, given the couplings and masses and things. But there's an interesting idea, which is that if cosmology is non-trivial, then this can have a sort of radical impact on the amounts of dark matter that your theory should predict. And so I want to look at this in 2 ways. Firstly, I want to look at scenarios where you have freeze-out dark matter, and you overproduce this. And then I want to think about ways that cosmology can actually reduce the amount of dark matter and bring it back into line. I'm going to think about these ideas of diluting dark matter with entropy injections, which is an idea which has been around for 20 years or so, but typically this has only really been applied to sort of the classic WIMP models, neutralino, for instance. And I want to talk about this slightly more generally, and I also want to talk about it in the specific context of freeze-out during matter domination. And in the second part of the talk, I want to go into a slightly different point of view. And rather than thinking about freeze-out dark matter, I'm going to talk about something called freeze-in dark matter. And I'm going to talk about, I'll sketch out what that actually means as a model for those who aren't so familiar. And then I'm going to talk about how cosmology can enter into these calculations and can lead to highly non-trivial changes in your predictions if you are in particular parameter regimes. So, why would we worry about these things is an interesting first question, and I would like to argue the answer to this is that if you write down the sort of simplest class models for freeze-out dark matter, you arrive at this WIMP picture. Now, the nice thing about the WIMP picture is that it tells you that dark matter should have some particular cross-sections and be around some particular mass range, so sort of hundreds to TeVs of masses, and a lecture week, or maybe somewhat lighter. Now, the most classic WIMP models are sort of things that are, for instance, Z-exchange or Higgs exchange that mediates the dark matter in the standard model. These things have been ruled out for quite some time. But you can start to think of slightly more general. Now I talk about WIMPs, meaning weak interactions, i.e. not that strong, rather than capital W for electroweak. And you sort of expand the range of models you'd like to think about. And this sort of red hue is sort of indicative of like the class of WIMP-type models. This is taken from a Snowmass report, the last one, I think. And so what you can see, which is quite interesting, is the range of WIMP-type models are highly accessible to the sorts of experiments that our colleagues are very good at running. So what you can see is over time we've slowly been pushing forward in ruling out this WIMP parameter space. This red line is sort of roughly where we are now. I think we're actually a bit lower, we're around here. And you can see you've rolled out a decent chunk, and arguably the most well-motivated chunk of this WIMP parameter space. And moreover, in the next 5 to 10 years, you're going to push down to these LZ experiment, for instance, is supposed to rule out both at least half, if not the majority of this, what I'm calling the motivated WIMP parameter space, but also particular bench point models, which particular people have pointed to as particular nice implementations of supersymmetric WIMPs. So that's kind of interesting. It's sort of very nice that firstly, we're getting information about the nature of dark matter. The simplest scenarios can't be constructed. The slightly more convoluted ones are going to be conclusively tested. So if we think with the sort of negative point of view that this is really not a discovery reach, but it's an exclusion reach, this should really push us to think about ways of circumventing these limits. And 2 ways to do that is, one is to relax the constraints, and the other one is to look at non-freeze-out dark matter. So, one way to relax these constraints is to think about how cosmology can impact these observations. So one thing you would like to do is you just sit down and calculate the amount of dark matter today from your given particle model. You can calculate its freeze-out abundance, and from that you can work out what omega dark matter is, which is the quantity that they go and measure. And what you find, it has some form like this. It depends on the mass and the number density relative to the entropy density. But what's interesting is, if you change the entropy density, whilst leaving the number density of dark matter alone, then this number can be drastically changed. And the way you would go about increasing S but leaving N untouched is you could have some heavy particle which has a significant chunk of the energy density of the universe, and you could have this thing decay primarily to standard model states and with no appreciable branching to dark matter. This way S jumps, but N dark matter stays the same, and you can parameterize this with some sort of dilution factor. So as I sort of said, this is sort of back in sort of 2000 and earlier, 1990s, these tricks were well known to play games about saving the WIMP or doing various other things. And in recent years, they've had some revival of this sort of asking what can this do when you think about a wider range of dark matter models. And that's sort of what I'm going to sketch for the first part of the talk. Now, if you have a particular idea, a particle in mind that's sort of is long-lived and has some appreciable amount of the energy density, you can actually extract fairly reasonable dilutions of this. So a way of thinking about what this dilution parameter is, you can think about it as the temperature that the thermal bath of standard model particles has after these states decay, which are diluting the dark matter, relative to the amount of the temperature that would be there had no decays ever occurred. And so this is a sort of simple way of parameterizing this dilution. It's the third power because it's the entropy which is changing. And an important point is the energy injection essentially does a new reheating event. So after these states have decayed and the bath is thermalized, there's this temperature which is different to the one which would be if there was no decay, and so you can define essentially a reheat temperature, which is associated to these decay events and not the sort of classic inflationary reheat temperature. Now, for a particular model, if you have some state of a mass of 10 to the 8 GeV or some benchmark mass, and it reheats to some specific value, then you can calculate what sort of dilution you expect. And what you can see here is that if I take reasonable parameter values, I can get extremely large dilutions. This is nice because that means that in the early universe, I can overproduce the dark matter and then adjust it with this dilution. Which means, in turn, that I can have smaller couplings and still match the observed relic density. The other thing which allows us to actually even contemplate this scenario is essentially our ignorance of early universe cosmology. We have looked at the standard model and we've extrapolated what we expect the milestones for cosmology to be going back in time. So at some point there was recombination, and then there was Big Bang Nucleosynthesis, and then going back in time you had the QCD phase transition, electron-weak phase transition, all the way back to inflation. However, our evidence for cosmology essentially stops around Big Bang Nucleosynthesis. Below this, we have essentially no real constraints in the scenario. Although we do, we have hints about that this inflationary cosmology stuff was at some point in the early universe. But really, this is around 10 to the 16 GeV, say, at its highest value, and BBN is around an MeV. So this is almost 20 orders of magnitude of temperature where you are free to actually inject new physical events, and provided that everything settles down by the time you get back to BBN and you recover standard cosmology, then you're good from an observational standpoint. So one thing you might like to do is you might like to consider a period in the early universe where the universe is not radiation dominated, but it's dominated by some other energy density, or other type of energy density. The most classic and simplest scenario is to consider an early period of matter domination, perhaps. So this is where I have, say, some heavy state that decouples from the standard model. As the temperature has dropped below its mass, then it becomes non-relativistic. and that changes the Friedmann equations, and ultimately it trickles down into changing the Hubble rate, which is interesting. So whilst in the sort of classic radiation dominated scenario, you'd expect the Hubble rate to go like the temperature squared, in this matter domination era, it goes like T to the 3/2. Now, the reason why that's interesting from the perspective of dark matter is that when you actually calculate what the dark matter freeze-out temperature is, you do that typically by comparing the annihilation rate to the Hubble rate. So if I parametrically change what Hubble is, then I change this relationship, and I get different answers. Another possibility I'll just highlight quickly, although I'll come back, is that if you have a state which is dominating the energy density and then it decays, if those decay products actually dominate the energy density of the universe at some point, then the Hubble rate switches over to this T to the 4 evolution. And this was an interesting point pointed out by, in this classic paper of G. Dietschy, Kolb and Riotto. And this actually sort of, the differences between these are interesting, but also the fact that these two scenarios imply that there is this entropy injection as well, which is needed when these states decay, or this state finishes decaying, then really you're seeing that cosmology is coming in and really altering your freeze-out condition. So I just want to say a few lines about what the difference between this particle decays period and matter domination is, just to really make that clear. So I can consider a scenario where I look at the ratio of the energy density of a given state relative to the total energy density as some function of time. So what I do is I consider a scenario where I have some state that becomes matter-like, but it contributes some small fraction of the energy density initially, and I have these other states which are my radiation bath. Now, a state which is matter-like in its evolution evolves like the scale factor to the third power, whereas the inverse scale factor to the third power, whereas the radiation goes like the inverse scale factor to the fourth power. So what you find is that over time, the contribution from the matter tends to grow to dominate the energy density. So this is what is shown here. Now, this is, at some point it dominates and it just sort of, this is a log plot, so, no, this is not a log plot, but you can't see the change anymore. Now, what you might expect is, after some time, all of these states just decay when I reach the lifetime of this state. But that's not strictly the way that particles decay. Typically, they decay with some sort of exponential profile. And so this is what you see as it falls off. And the important thing here is that because you have this exponential fall-off, in principle, there's a point where the decays due to these particles to the thermal bath have to be included in the Boltzmann equations of how the thermal bath is evolving. So that is incorporated by some sort of term which goes like the energy density of this state times its decay rate. Whereas in this earlier period, there is no, essentially this term can be neglected because these exponentially suppressed decays, so it has a negligible impact. So I'm going to refer to this scenario where decays can be entirely neglected as the matter-dominated scenario, and this latter scenario where you have to incorporate these decays, because they are important, as the decay era. Now what's interesting is the decay era had been well studied in these papers of G. Dietschy, Kolb and Riotto and the papers which followed it. But actually, studies in this regime where these terms were entirely negligible had been largely neglected. And one reason why this scenario is much nicer is because all of the technology that we use to do radiation-dominated freeze-out carries through almost trivially. Whereas when I'm in this regime here, where I have these decays present, they actually lead to entropy non-conservation in the thermal bath. And so you actually, to do the analysis carefully, you have to adopt very clever changes of variables to adjust for this. So I'm going to talk about this one scenario here, essentially as a benchmark for showing how much cosmology can impact thermal freeze-out. And I'm going to apply it to a couple of models after sketching the sort of general principles. So, as I just mentioned, in this matter-dominated case, I can follow essentially something similar to what you'd find in Kolb and Turner, but where I have to just make a few small tweaks. So I write down my Boltzmann equations, and I can define a Hubble rate now, which sort of interpolates between the classic radiation-dominated scenario and the matter-dominated scenario. And I do that by defining some parameter r. When r is 1, then I am in the radiation-dominated case, and when r is 0, I am in the matter-dominated case. I also define some parameter t star, which is defined as the temperature at which this state chi becomes matter-like. So, as a sort of benchmark, if the temperature, if chi is thermally coupled to the standard model in the early universe, and then when it decouples, it maintains the same sort of temperature relationship, you can think about the threshold T star at which it becomes non-relativistic to be around the mass of that state. Now, if this chi was never really in thermal equilibrium and it has some independent temperature distribution from the standard model, then this is essentially a free parameter. But I'm going to stick with this simplest. Well, I'm going to leave this as a free parameter generally, but the simplest scenario to think about is this being the mass threshold of this particle which will later decay. So with this in mind, what you're really doing now is you want to compare the Hubble rate with the annihilation rate, and I can just derive the similar sort of freeze-out condition and the yield at freeze-out, just as I would in the radiation-dominated case, and I'm going to extend this to the matter-dominated case. So the important points here to take away is that the freeze-out temperature in the radiation compared to the matter-dominated case differs by a change in the power of the mass. Although note, this is inside a logarithm, so the impact is small, but if you consider regimes away from the WIMP case, this can be appreciable. But more importantly, there's a T star dependence that comes into this relationship. And so by picking this to be different, you can actually change the freeze-out temperature by some reasonable order 1 factor. I say order 1 because it's inside the log again. And similarly, this falls through when I look at the yield. What I find here is that it has a slightly different dependence on xf, which is the inverse scaled freeze-out temperature, and it's also an x star that comes in here. So this here is coming in this case, it's not inside the logarithm, so the x star can have a larger impact here. So
x is the temperature in units of
mass.
This is m over t, yeah.
M over T.
Yeah. Dark matter mass over t. So let's see how this sort of all falls out. First in a simple example, and then in some specific models. So I'm going to do the very simplest thing I can think of, and I'm going to parameterize the the annihilation cross section as alpha squared over m squared, m dot matter squared. And I'm simply going to ask, what contours do I need to get the correct relic density today for, firstly, the radiation case, which is shown as this dashed line, and then 3 different values or 3 different scenarios of this matter-dominated case, where I'm assuming that my dilution factor is, say, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. So again, this can be, at this point, this can be picked somewhat freely, because it depends on additional inputs, like the reheat temperature and the mass of this state. But what you can see here, immediately, is that, firstly, I have slightly different gradients in these things, but there's not a great effect. But as I increase the dilution, then my couplings can become significantly weaker, and this is going to allow me, when I come to proper models, to evade direct detection constraints and other constraints. However, there are a couple of consistency conditions we should just mention first, before I go any further. So you could do a very, very general analysis where you look at freeze-out in each regime. You could look at freeze-out when it happens before you enter matter domination, during matter domination, and after matter domination, depending on when this state decays and does the entropy injection. But that's good. That's a little convoluted. So to simplify the analysis and really draw out the salient details, we're going to look at the scenario just when this freeze-out occurs during this period of matter domination. And that essentially means that the state has to dominate the energy density, and so should be sufficiently long-lived to do that. The freeze-out should occur before the decays of this state become appreciable. The reheat temperature should be such that I reheat above BBN, so essentially I recover standard cosmology, and I want this to give me cold dark matter, so I'm going to require that the freeze-out temperature is sufficiently high. Now, we can apply this to a set of specific models, and the models we should choose, I think, are probably the most elegant ones and simplest ones we can write down. The most elegant model to my mind, or simplest model to my mind, is the so-called scalar Higgs portal. It's the idea that I take the standard model, I add a single scalar field, which is the dark matter, and it couples to the standard model just by this mixed quartic interaction. So it's a h squared phi squared vertex. Now this is a beautiful model because it's both highly minimal and highly predictive. In particular, with this coupling, you can extract the relative annihilation rates to the different standard model products as a function of its mass. So you can see here that as I make the mass larger, these things go around, say, 10 GeV. These things are going primarily to B's as I go up to 10 to the 3, so 100, 10 to the 3 TeV, sorry. I'm going primarily to W's. I can also look at, for instance, this plot down here is actually just the total rate, so you just sum these different contributions up. So this is a beautiful model. Its beauty is also its downfall because it's highly testable. And people have gone away and tested this under the conventional assumption of freeze out during radiation domination. And this, what you find is this one free parameter, the coupling and the mass. But as I change the coupling, the relic density is reproduced along this black line, with the dotted line being one is real and complex. So there's a very close, unique relationship in this case between the mass and the coupling, and you can actually place bounds on this. And this has been done. So in particular, I'm bringing up this paper by Berlin, Hooper, Lin, and Escudero. And what you see here is all of this parameter space is essentially excluded apart from right on the resonant tip, where I'm doing resonant annihilation of dark matter to standard model states.
So what's the real and complex?
It's whether it's a real scalar or a complex scalar. So it's just a degree of freedom. That's just the factor. So this is a great pity, because this was an elegant model. Well, maybe you think it's a great pity. I think this is a great pity. It's an elegant model which has been excluded rather than experimentally verified. But we can recast this in terms of this matter-dominated freeze-out, and by doing so, we gain some additional degrees of freedom. We gain, for instance, this T star, which is when this state goes non-relativistic, and we gain a point of freedom, which is how much entropy injection dilutes the dark matter. And so, if I place these on a plot, I'm now showing the same coupling, single coupling kappa, and the same dark matter mass. Now, these are contours of the reheat temperature for which the correct relic density is obtained. Now, the reheat temperature essentially here is a proxy for the dilution parameter. It's slightly more useful to state this in terms of the reheat temperature because it gives you a better intuition for the evolution of the universe, and also you can start to see how close you're getting to Big Bang Nucleosynthesis.
This is reheat following this matter domination.
Exactly, yes. So from following decays of this state. And so there's some regions here which are the sort of consistency conditions I showed earlier. This region up here essentially...
Just to make sure I'm following
yes.
all this, so in addition to the particle coupled to the Higgs, there's another particle that brings the universe into matter domination.
Yes. And that particle primarily couples to the standard model.
Okay,
its
right.
couplings to the dark matter need to be negligible.
Yes, right.
So it's true, I have gone up by one additional degree of freedom, but in doing so, we've revived this model. So this red space is showing essentially where these conditions are being satisfied. Either I'm not reheating, freezing out before the reheating occurs, or I'm running into hot dark matter. And so I really want to live in this white space. And this is for some specific choice of T star. There's another choice in our paper if you're curious. But I haven't put any direct detection bounds on this yet, or similar bounds. So what I'm going to do, so it's not too overcrowded, is I'm going to shade out these consistency conditions, and I'm just going to show in the coloured lines the various experimental exclusions. So now, what we see in this parameter space is xenon 1 ton, which was excluding a lot of this region, is coming in over here. We've also included a region from indirect detection. This is the Fermi search for, I think that it's the dwarf toroidal search for dark matter annihilation to BB bar. And what you can see is that this region, parameter region here, and this parameter region over here, which are the consistent regions, they all lie below the experimental limits. Now there's one other line on here, which is the neutrino floor. The neutrino floor is this idea that once you can push your dark matter detection experiments to a sensitivity such that there is an irremovable neutrino scattering background. And so seeing dark matter events in this region of parameter space is difficult. It's an unresolved problem how you make progress in that direction. But there's also a regime over here which is above the neutrino floor and is potentially testable in future experiments. So this is very nice, and so what we've done is we've played a trick in cosmology and we've revived one of our favourite models of dark matter. Now, I'm just going to show this for two other models which are also very beautiful. I'm going to go through them a bit quicker since I've sort of explained the basis. The next one is I point towards is the fermion Higgs portal.
Sorry, can I
Yes.
just want to understand why that happened, because naively, very naively, you've diluted the dark matter, right?
Yes.
So somehow you would think that it would be more difficult to detect, right? But
Yes.
so why is it that now you've got more parameter space above the neutrino floor?
No. I've got more parameter space everywhere, just some of it is...
Yeah, but
Well,
particularly, above the neutrino
I mean, there was
floor, before you didn't have, before you
This
get
was-
above the neutrino.
Here was the neutrino floor, so...
Right, but for the model to be above the neutrino floor, you had to be in this really, really narrow range, right? Now you've got a bigger range of the model where you're above the neutrino floor. How does that happen?
So to a large extent, this is scaling this curve. So as I do an entropy injection, this curve is being scaled down by an order of magnitude.
Why does it scale down? Why do you have more?
So I'm allowed to overproduce the dark matter in the early universe because the dilution event will allow it to be diluted. So I can have smaller couplings and still match the relic abundance.
Oh, I see.
There's some small additional changes like changes to freeze out temperature and things like this, but that's the largest effect.
Right,
And
I
so,
understand.
yeah.
Right, so the smaller coupling, the point is those same small couplings are appearing in direct detection,
Yeah,
but now you can use those smaller couplings to get a bigger amount of...
precisely right.
Yeah,
Yeah.
that makes sense. Thank you.
So let me point out the next scenario, which is perhaps the next most minimal, is this thing called the fermionic Higgs portal. I have a fermion dark matter that couples to the Higgs. This is dimension 5, so I should introduce some cutoff to make it dimension 4, the whole operator. Now, this has a benefit and a con. The benefit being that this is a light fermion state, which light compared to the Planck scale, which is therefore better understood in terms of naturalness. The con is that I've introduced this effective field cutoff. I've got a non-normalizable operator parameterizing this, and therefore there should be some new physics, and there's some essentially could be some, it's not a complete theory. That's the correct way to say this. But just taking this as it is, you could of course go ahead and write a complete theory and do the same analysis, but this is the most general way to do this. I'm going to parameterize an effective coupling by V naught over lambda, and plot this on the left axis, and then I have a similar story. There exists white space below this, which is both theoretically consistent and evades xenon 1 ton, and this is over a fairly large mass range. Again, I'll highlight that this is a scenario which is largely excluded in the radiation-dominated case, which we actually plotted the dashed line, which is the radiation-dominated case, and you actually just can't see it on the plot because it's all up here. Again, some of this stuff falls below the neutrino floor, which is unfortunate, but nature may just not care about us being able to see dark matter in direct detection experiments. And the last thing, which I point out because, again, it's one of the most minimal dark matter models you can write down, is dark matter which carries, or is an SU2 representation, essentially. So it couples to the standard model Z. And the simplest way to couple something to the standard model Z is for it to be a vector-like fermion. If it's not a vector-like fermion, then you have to worry, so if it's chiral, you have to worry about cancelling gauge anomalies and stuff like that, everything's a mess. But for the vector-like case, it's super simple. And I can define a single kappa which goes through which has the vector piece and the axial piece, it's the same. And again, in this, we can evade direct detection bounds. The reheat temperatures are typically low in the models I'm pointing out. That's the one sort of generic feature that runs through all of this. But it's very nice that we've sort of revived these three classic models using this trick. Oh, actually, I forgot to update the archive number. So let me point out one last thing. This is going to, with connection to freeze out, because it's going to come up later in the talk. And really, it's also just a very quirky sort of model that these guys were thinking about. So in a nice paper by Dirano, Ferrandes, and Profumo, they considered the scenario where I don't have a matter-dominated era in the early universe, but I have some sort of, let's call it exotic era, where the energy density redshifts like, that should be minus n there. Rho phi evolves as a to the minus 4 plus n. Now, if I take m to be 0, this is going to give me radiation. Essentially, it's as radiation-like. If I take n to be minus 1, this gives me matter domination. But I'm going to just take m to be general. And something else people often define is this thing called omega, the equation of state, and I can write this down in this sort of form. Now, I won't take questions on this because I'm not. It's very tricky and possibly controversial how you write down a model like this. But these things show up in some quirky cosmology. They show up in tensor scalar theories. Supposedly show up in theories of cyclic potentials. And also, these people wrote down an explicit example which gives this. Now, there are some quirky features, like it has it's a negative potential if you take omega larger than 1. There are some worries about superluminal propagation in these models, which the authors claim are resolved. But I gave this talk in Berkeley last week, and these things came up as particularly contentious points. But I'm just going to show this as sort of an interesting parameterization, because it lets you think about what if the Hubble rate, or the Hubble dependence on the temperature, goes like some arbitrary power. Now, I sort of explained before, because the Hubble rate and it is implicit in determining the freeze-out condition, you change the way your predictions for what you expect. And so these are taken from this paper again. What they point out is that as I make the expansion rate of the universe faster and faster and faster, faster than radiation, I come into these interesting regimes where instead of getting a smooth switch off from exponential suppression in the number density to constant, I get these drawn out, what they call relentless phases, where these relentlessly annihilate. So it's kind of cute, but I'm going to keep this idea that you could parameterize the Hubble rate by an arbitrary temperature, because I want to come back to this question a little bit later, or this idea a little bit later. So that's the end of the first part of my talk. The sort of central idea was that if you write down a particle physics model which overproduces in the early universe, cosmology can correct for this and bring your models back into line with either the correct relic density and also potentially avoiding constraints. In the next part of the talk, I want to think about an entirely different approach to dark matter, this thing called freeze-in dark matter, which is a kind of neat idea. So, in the freeze-out picture, you initially have some thermal abundance of dark matter, and it annihilates, and when it stops annihilating, whatever's left is called the relic density. There's a different way of thinking about this, where I initially have zero dark matter, or negligible dark matter. But there are processes in the thermal bath which allow me to produce these states, and slowly I sort of drip energy into the dark matter states until this production switches off. And then whatever I've produced is my relic density. So this is interesting primarily because the parametric dependence of the final abundance is very different to the freeze-out case. So essentially it's inverse. So this is the freeze-out, and this is the freeze-in, where this is the annihilation cross-section, and this is the production cross-section. There's one other scenario, which is something called, this is often called IR freezing, and specifically it requires that you have renormalizable operators. There's an interesting scenario when I have a non-renormalizable operator that couples my dark matter to my standard model. So if there are only non-renormalizable operators, then even if there will be some energy leak transmitted via these things, the way to think about this idea of non-renormalizable operators is saying that whatever mass scale is suppressing this non-renormalizable operator is above whatever the highest temperature that the thermal bath reaches. So these operators were never possibly on shell, and moreover, as the temperature drops, they become increasingly more off-shell. So the best time to produce dark matter through these things is in the highest temperature part of the scenario. And so that's why you see this strong switch on. And for a dimension 5 operator, which is the only thing connecting these two sectors, the hidden sector and the visible sector, then this goes like the reheat temperature. And as I make the dimensionality of that operator higher, then it goes like a larger power of this reheat temperature. So, there's one last thing to note about these models, which is that there's an underlying consistency condition, which is the rate of production of dark matter should not be so great that I come into equilibrium with the thermal bath. The reason being is that if I start with no dark matter and I produce it until it's in a thermal abundance, then it will stay out of thermal abundance for a while until it hits the mass threshold, and then it will go through a freeze-out process. That is totally fine and consistent mathematically. It's just kind of boring from a physics standpoint, because all you've done now is you've written down a freeze-out model with a convoluted history. But this is interesting, because it tells you that if these objects, or this dark matter cannon never comes into thermal equilibrium, then it should be very weakly coupled. For a GeV dark matter with a renormalizable operator, these couplings are typically around 10 to the minus 7 or less to get the right relic density. And that's interesting because it's very small coupling. And so these things do not show up in traditional direct detection or indirect detection experiments. And you need to think of like new dedicated experiments to look for these things, or to have particular types of astrophysical systems that could lead to indirect detection signals. But so the first thing I want to do is actually sketch this idea. Now I want to tell you how you can be in a scenario where you actually do all those calculations completely wrong, because that's interesting. Now, in particular, I'm going to focus on this thing called the ultraviolet freezing scenario. So this is the idea that I only have a non-renormalizable operator, and I'm going to assume that the lowest order operator which connects the dark matter and the visible sector is of mass dimension 5 plus n over 2. Now, I will say now immediately that this is not my favorite parameterization of this, but this is the one which exists in the literature, so we're going to stick to it. That means that my production cross-section goes like t to the n over lambda to the n plus 2. So the reason we like this parameterization is because it essentially tells you what the power of the temperature dependence is. Now, when I calculate what the yield or the final abundance due to this UV freezing is, what I should do is I should take the cross-section and then I should integrate it from the reheat temperature, the highest temperature which is reached by the bath, essentially, to some lower energy limit. And what I find is that this picks up some strong reheat temperature dependence. This works well in some cases, and what I'm going to show in the next few slides is this works very badly in other cases. And the thing I've been a bit quick to say is that we've made an assumption here that T reheat is the sort of normal, instantaneous decay of the inflaton reheating temperature. That means I can write it down as like the geometric mean of the decay rate times m Planck. And what's interesting is that if this operator dimension becomes too high, then I become more and more UV sensitive, so more sensitive to higher temperatures, and at some point you actually become very sensitive to the details of the reheating process. And so this was first pointed out in this nice paper by Garcia, Mambrini, Oliver, and Peloso, who looked at the scenario of a transition from matter domination to radiation domination, and showed that if n is greater than 6, which I think is dimension 9 or above in mass dimension of the operator, then you can get a parametric enhancement of the dark matter abundance that then you would find from this naive calculation where you just put down this simple approximation for the reheat temperature. And I'll explain why that's the case. So this is essentially in terms of, if you were to plot the number density, you can see here in these set of plots that as I make the dimensionality of this operator larger, from n equals 4 to 6 to 8, that the primary point where production is happening is being pushed further back to higher temperatures. This point A, you can't quite make it out here, I think, but this is the point. This is T reheat essentially. This is the FRW scale factor at T reheat. So you can see at this point here, then you can see that most things are happening around T reheat or shortly after, but as I make my operators larger, then they're very much before T reheat. And that means this is, as I say, sensitive to the details of the decay of this object. So I'm now going to take what I want to do is take a slightly more adventurous view than the one taken by Keith Oliver Company. And I'm going to consider a state which has some arbitrary equation of state. So this is sort of motivated by this nice paper of Profumo, where they had this Hubble ray with some arbitrary temperature. Now, I can write down the evolutions of the energy density for the phi state, which is going to decay. I think I may have changed notation, actually. Chi states decaying at the start, and phi states decaying now. But hopefully that doesn't throw anyone off. And I have the evolution of the radiation component. Now, I can rewrite these in a way that I can just track how the radiation density, energy density, and the phi energy density, and the change with time, or FRW scale factor, and I get some expressions like this. I have pictures in a second, which will replace these. And what you find is there's this interesting temperature. This has actually been known from the early paper of Giudici, Kolb, and Briotto. There's this interesting temperature evolution in the thermal bath. Now, essentially, you're assuming, the idea is that you're assuming that you start with some sort of inflationary cosmology where your radiation bath has essentially gone to a negligible value. That means it has some negligible temperature at the start, and as this state phi starts to decay, it starts to produce these radiation particles, which thermalize and make some temperature, and that leads to a temperature growth. Now this temperature growth continues until some point, where essentially the point is when the energy density in the decay products of this phi, decay products of this phi, have more energy density than the phi particle that's decaying itself. Now at this point you get a switch over in the behavior, and you find the temperature starts to fall. Now what's interesting is that this switchover, when the highest temperature is obtained, is not the reheat temperature, but is a temperature which is typically higher than the reheat temperature. If the reheat temperature goes like the square root, here I'm defining the reheat temperature as the square root of the decay rate times m Planck. This Tmax is characteristically something that looks like this. It goes like some initial Hubble value, which essentially is a free parameter, the Planck mass, and the reheat temperature squared. But this is interesting because it tells you that if your freeze out is sufficiently UV sensitive, i.e. you have a very high dimension operator, the thing which should be coming into the top of this integral when to calculate the abundance is not the reheat temperature itself, but it's actually this maximum temperature of the thermal bath. And this can have significant changes, because this thing is actually sensitive to the initial equation of state of the system. So, if you actually look how the number density now changes in this system, you can show that the number density as a function of temperature depends on this Tmax quantity. It's a complicated expression, but the one thing here is it depends on this Tmax to some power. And if I define this thing called the critical number, n, So this n here, recall, is parameterizing the dimension of the operator. Then the dependence on the evolution of the amount of dark matter goes like t to the n minus n critical, where n critical depends on the initial equation of state of this phi particle. Now, the classic example is sort of this transition from matter domination to radiation domination, which means omega equals 0. And so if I put omega equal to 0, I find that this critical n is 6, which coincides with the Keith Olive paper. But if I'm willing to see the more general equations of state, then this becomes an interesting free parameter. Oh,
What happened?
I think I pressed next with too much enthusiasm. Let me just take it out and put it back in. It's not big. Just thinking about it. Oh.
What happened?
Switch.
Hey.
Switching.
Good. So let me convert this n into a yield, and the other thing I'm going to do is just look at the amount of dark matter I would have, assuming this approximation of instantaneous reheating. So essentially, all of the phi states decay instantaneously. There's none of this question about what is it dripping in energy, how is the temperature in the thaw bath evolving. I'm just doing the very simplest calculation that people have done in the past. And I'm going to compare that to this more careful calculation, where you do look at the temperature evolution, you identify that there's a higher reheat temperature, and I'm simply going to ask, if I take the ratio of these two things, how wrong is my naive calculation? And so I'm going to find this boost factor. Now, what you can see here is there's a couple of regimes. If your operator that you've written down is smaller than this critical number, then what you find is that the simplicity you write down only changes by some small factor. 10%, order 1, something not particularly interesting. There's an interesting threshold case which gives you a log, but more interestingly, if I take the operator dimension larger than some critical value, then what I find is that there is an enhancement in the expected abundance of dark matter that goes like the ratio of Tmax by T reheat, which in simple models or typical models could easily be a factor of 10 or 100, to the power of n minus nc. So this means that for matter domination, when nc is 6, which corresponds to, I think, to a dimension 8, dimension 8 operators given enhancements, then if I write down a dimension 10 operator, then this can give me a large factor of 10 to the 6 or higher. Let me just reparameterize this because it's going to be helpful for 1 second. I can think about this in the converse sense, which is, what if I know my operator dimension, which is transferring energy from standard model to dark matter? Then I can ask, what is the boost for the naive calculation to the careful calculation if for different omegas, so different equation of states, or put another way, different Hubble rates, initial Hubble rates. Now what I find is that, again, if my omega is greater than some omega critical, which now is a function of the dimension of this operator, the connector operator, then again I get some enhancement that goes like Tmax over T reheat to some function. So the easiest way to see that this can have a large impact is with a plot. And so here I'm looking at a plane which is, better to look at this side I think, the mass dimension of the operator which connects the standard model and the dark matter. And on the x-axis is the initial equation of state. So a couple of points benchmark points. Omega 0 is matter domination, omega 1/3 is radiation domination, omega 1 is, for instance, something called conation domination, if you're relatively familiar with this. And this dashed line essentially indicates where our sort of standard models of cosmology end. And in this parameter regime where omega greater than 1, this is where the expansion rate is faster than sort of we typically expect to find in normal models that we write down. But there are examples in the literature where you can find omegas greater than 1. You have to be very careful about that everything isn't, there's nothing going quite awry. So there are some worries I mentioned earlier about superluminal propagation in these scenarios. I'm not an expert, to be honest, to say which models are well justified and which models might be a bit quirky. But there are certainly very good people who have written down models in these scenarios and areas, and so I put this up as an interesting extension of this parameter space, and also because it allows for much larger impacts on the relic density. So this plot essentially is showing you the enhancement you would expect, so the boost factor, for an assumed value of Tmax over T reheat, as I change my mass dimension and omega. And so what you can see is that for large mass dimensions, you could get factors of 10 or 100 or 1,000, depending on the omega. But if you really allowed me to go to these sort of non-standard cosmologies in this sort of heavy dragons territory, then the impact of the dark matter abundance from this careful tracking of the highest temperature of the, or rather the details of the inflationary heating, allow extremely high changes in the calculated number density. The last thing to point out is that whilst this is interesting from a mathematical standpoint, we would of course like this to maybe solve a problem. And there's a particular nice example which actually in our paper we give 2 or 3 examples, but there's one particularly nice example which was first highlighted by Keith Olive and collaborators, which was this idea that consider a supersymmetric universe, but with this is high supersymmetry. So I'm assuming that my superpartners typically are PeV scale or above, and the only low-lying state is the gravitino. And the gravitino, it doesn't matter so much what its mass is, but it's importantly, the reheat temperature lies below the typical superpartner scale and above the gravitino mass. This means that interactions in the thermal bath can't produce the heavy particles, but they can produce the gravitinos. But these gravitinos necessarily have to be pair-produced. And what Keith Olive and company point out is that this is an intrinsically, the production is via a dimension 8 operator, and so this puts you in this particular regime where you start to pick up these large enhancements. The other thing which is important to note in this scenario is that because it's the gravitino and the only production is direct gravitino pair production, this is an extremely suppressed cross-section, so it would be naively expected to having, at the very least, to be underproduced, but more likely to have a fairly small abundance. So this is one scenario where you can use a nice cosmological, I'm going to call it a trick, to enhance a motivated dark matter candidate's abundance so that it can match the dark matter relic density that we observe. And that brings me to my conclusions. So, there's a few things. So the principal thing I've been trying to sort of stress in this talk is that this idea that you write down a particle physics model and you can immediately calculate the relic abundance is a bit quick, because cosmological events can drastically alter your expectations. Not only that, I mean, these sort of cosmological events, like early matter-dominated periods or entropy injections, are quite well motivated from the perspective of beyond the standard model physics and also string theory. What's nice about these cosmological events is that they can bring models that you would naively expect to be problematic back into the fold. They allow for heavier dark matter and potentially for smaller couplings. And using these ideas, it was shown in this talk that you can use these to revive classic Higgs portal models and also Z-mediated dark matter, which are some of the most elegant dark matter explanations or models that we have. The latter part of the talk, I pointed out that there are some careful details that have to be taken care of in these models of UV freezing, and showed that they can give you a nice way of actually addressing the underproduced dark matter via this mechanism. And so yes, I think there's lots of interesting applications, and if you have a particular model that you like, but you think it's excluded by direct detection, then these sort of papers present a set of tools for dealing with that. So, thank you for your attention.
Any question?
So can you go back to just a few slides to the omega plot? So
this one?
Yeah, just that one. So omega equals 0 is just is a transition to radiation domination, right?
From matter domination to radiation
from matter
domination.
to radiation
Yeah.
domination. So if I'm just trying to understand. So and then because it just went by a little fast. So then,
sorry.
So I want to understand. So omega, when omega is larger than 0.
So omega
are you
third
always
is
assuming that you're going to radiation domination
yeah.
and you're changing the phase before?
yes.
So I can kind of ask, on one side of 0, it's expanding faster than it would for omega equals 0 before matter domination. If I'm normalizing to today's, is that a way I should think about it, or vice versa?
Yeah. So I mean, so you should think about it as expanding faster than radiation. So radiation domination is omega's a third.
Yeah.
So a third is kind of around here, right? So on this side, I'm expanding faster. Wait, slower.
Which way? Which way?
This is slower. So
Bigger than 0 is slower.
no, yeah. Well, because I'm normalizing to radiation domination.
Right. Yeah. So bigger than 0 is you're expanding slower before the transition, and that sort of explains why you're getting more dark matter, right? You sort of, if you're expanding slower, it makes sense that you would be getting more dark matter, right?
Let me just think about that for a second.
Because you're doing freeze-in, right? And so the longer that,
Yeah, that's correct.
I just want to know if I'm thinking about this right, because I want to understand this at least qualitatively. If not, please correct me.
I think this direction is sourcing a faster expansion. Is it not?
I don't know. I mean,
That was my recollection.
You go back to your.
At high temperature, going back to high temperature. If you're scaling from fixed temperature, certainly, the omega higher, and you'll be at faster expansion rate earlier.
As to what, so let me just think about
So
why
then-
this is the
then-
case.
I just want to just understand it qualitatively.
Yeah, I haven't really.
So
I
let's see,
should have.
what's the definition of omega again? It's t. It's appearing in some power of t somewhere.
Yes, here we go. So you can write it in this way as
It's W, for this extra field.
Yeah,
Yeah.
I'm not used to W. That's fine for you, but so W
Oh,
is
sorry.
M.
So I would
M
tell-
is large, so M is the power in the expansion.
exactly.
Before.
But I'm missing a minus
so
sign.
M is large. Okay,
Just-
but
just
I'm
take
just
that.
looking at the Hubble case. So
Yeah, the
Hubble
Hubble
goes
case.
like T to. It goes as a bigger power of T for large M.
Yes.
There's a bigger power of T for large omega. So in my language, it's expanding faster. Yeah, for larger omega.
Mm-hmm.
So then why
Yeah.
are we getting more? Because we're in this.
It's a good question. I'm trying to think myself.
I mean, this isn't the sudden approximation, so there's no shenanigans with.
No.
During
This is
reheating.
the ratio of the. This is the ratio. The
But
ratio.
You're using the sudden decay approximation.
I'm not using. I'm precisely not. This is what these.
Okay, so
these
it actually
numbers-
has to do with some particular. You have some finite length of time for the reheating thing, right?
Yes.
So that's maybe that's where that's coming from.
Maybe that's where it's coming from. It's a good question. I will try to think about it. I don't have a good intuition as to what's driving this. Let me go back. Let's stare at some equations.
It's if you kept everything else fixed and you just made the universe expand faster
Mhm.
earlier, keeping everything else fixed, I would think that you'd always produce less freezing dark matter. So I mean, it must be a question of what else you're holding fixed. Like you're holding fixed the time period or something that you're reheating, and then somehow the
I mean,
faster...
there's some complicated. I mean, there's some complicated Boltzmann equations, right? So the omega factor is entering as an exponent in both the evolution of the phi energy density and also the evolution of the radiation energy density, because because one is sourcing the other. It's not entering into the dark matter though, so.
I mean, Friesen is a completely one-sided thing, right? I mean, you just produce it and then it shuts off. I mean, you're always adding dark matter,
Yes.
but something eventually shuts it off. It either shuts off in the IR
Mhm.
or in the UV. So, it's just, it's okay. Anyway,
So
it's all
I
right.
think the
just
critical
wanna
point
make
here is
up
actually that. I think the critical point is. No, I don't know. I need to think a little bit. Why? I agree that you would expect.
Was this related to the dimensionality of the operator?
I mean, so the dimensionality of the operator is on the y-axis,
Oh.
and the
So
integration
just-
state is on the
focus on one
x-axis.
of the curves.
It's a very good question. Maybe we talk offline. I have some more plots, which might be insightful.
Okay.
This is a good question. Any other questions?
So no question. Thanks, Bill, again.
Okay. No, I could leave this actually and see what we can find.
Do you have any gravitational wave
It's an interesting question.
signature for this kind of stuff?
I haven't really.